So welcome to the question of articulation point. So what is articulation point? So what is articulation point? What is articulation point? So according to us, articulation point is defined as when we remove any node, when we remove any vertex like this at this stage, when we remove the two. So at this stage, when we remove this two, then this graph is divided into two parts. So this is our articulation point. How? When we remove this two, then this graph is divided into two parts. Then this two is our articulation point. Okay. Then this two is our articulation point. Okay. When we remove this two, then the graph is divided into two parts. Then this two is our articulation point. After that, after that, what we are saying to you, if we remove this four node, then this graph is this graph can be divided into two parts. What do you get? No, this graph is not divided into two parts. This is not our articulation point. This is not our articulation point. Okay, so this is not our articulation point. Okay. So this is our not a articulation point. Clear? So the articulation point is the point where when we remove the vertex, then the graph is divided into two parts. Then that vertex is called the articulation point. Okay. So how we can find articulation point? Before find articulation point, we have to find the three things. First is parent array. Then the second thing is our low value, discover value array. And the third thing is the first is a parent array, the second one is a discover value array, and the third is called as a low value array. Okay, so this is your parent array, this is your discover value array, and this is your discover value array. Okay, so this is a dependency. This is the three thing when we are going to find the articulation point. The three parts is needed to find the articulation point. Okay, so first we are discuss about parent array. So what is parent array? So this is our DFS. So in this stage, in the term of find the articulation point, what we have to find? We have to find a discover value array. Okay, so in this part we have to find a discover value, articulation point. Okay, so how we can find articulation point? So for finding articulation point, we need this three things. Okay, so we are going to discuss about parent array. So for find and parent array, we have to use a DFS in this graph. So what is the DFS? DFS is like depth first traversal. Okay, so initially one is called 3 is called 4 is called 6 is called 2 is called 8. So everyone is called its neighbor. So at this stage, the 1 is a parent of 3. And we suppose the 1 is a parent of 3 and 3 is a parent of 4 and 4 is a parent of 6 and 6 is a parent of 2 and 2 is a parent of 8 and 8 is a parent of 3. So the parent array is formed according to its call. Like when 1 is called to 3, then the 1 is parent of 3. And when 3 is called to 4, then 3 is a parent of 4. And 4 is called to 6, then 4 is a parent of 6. And we store all values in a parent array. We create an array and then store at this stage, when we call this neighbor, we store the parent of neighbor or is source. What I'm saying, if we call this 3, then we find out which one is our parent. We find out this neighbor is our parent, then we just store the parent of this. Parent of this one is 3. Sorry, parent of 3 is 1. We store the parent of 3 is 1. Okay, in the array. Okay, so this array is stored as a parent array. Okay, so this is all about parent array. This is all about parent array. Okay, so how we can find an parent array? Okay, so this is our parent array. So after the parent array, what we have to do? After the parent array, what we have to do? Another thing. So after the parent array, what we have to find? We have to find a discover value array. So what is the discover value array? What is the discover value array? So I am going to discuss about what is the discover value array. When we call from one depth first traversal, in the depth first traversal we call our neighbor 3, we call our neighbor 4, we call our neighbor 6, we call our neighbor 2, we call our neighbor 8, and we call our neighbor 3, and we call our neighbor 7. And then we backtrack it. And we explore another path, and we explore another path. See, so when we backtrack it, then we goes to another path, then we comes back. So when we discover any nodes, any vertex, like when we call the one to add, like what is the discover value? Discover value is something like when the vertex is discovered. When the vertex is discovered, what is the stage? Like what is the stage value of 3? What is at which stage? At which stage the discovered this vertex 3 is discovered? This is the stage of 1. This value 1 is this vertex 1 is discovered at the stage of 1. And this is the discovered at the stage of 2 when we call in DFS, and this is discovered at the stage of 3, and this is discovered at the stage of 4 in recursive call. In recursive call, the stage of 1 is discovered as a stage. It means the 1 is discovered at the first stage, and 3 is discovered at the second stage. The discovered value of 3 is 2. So this is the stage where the value is discovered, okay, where the vertex is discovered. So this is the discovered at the fifth stage, though. So the discovered value of 2 is 5. So same here, the discovered value of 1 is 1. The discovered value of 3 is 2. So the discovered value of 4 is 4. The discovered value of 6 is 5. The discovered value of 2 is 6. 1, 2, 3, 4. Sorry, I am just create a mistake, but I am going to improve it. So the discovered value of that stage is 3. Okay, so same here. The discovered value of that stage is 4. Same here, we create a mistake. So discovered value of that stage is 5. And the discovered value of that stage is 6. And the discovered value of that stage is 7. And the discovered value of that stage is 8. Okay, so this is our discovered value, that where our node is discovered, that at which stage our node is discovered. Okay, so you just clear about now. When we call it DFS, when we calling a DFS, then the vertex is discovered at this stage is called a discover value, and we store the value in array. It's called a discover value array. So we figure out what is our parent array. Sorry, we figure out what is our parent array, and we figure out what is our discover value array. So after that, after the all conditions, after the all calls, what is our low value array? What is our low value array? So I am going to explain what is our low value array. It is something was tricky. It is something tricky, but I am going to explain it, okay, in a clear manner. So this is our discover value array, this is our parent array. So discover value array is something like when this vertex is discovered in calling of DFS. At second stage, so how we can find out discover value array? Discover value array, we just take a global value and we increase the value when we call in DFS. Okay, in the time of calling, we increase the value of the global value. So the value is stored as a discover value array. After that, how we can find this low value array? How we can find this low value array? Okay, this low value array. So for find a low value array, what we have to do? We have to just go at this stage. Okay, so what is the condition to find a low value array? The first condition, the vertex should be point a minimum discover value. First condition, the one vertex should be point a minimum value. Should be point a minimum discovered value. But second condition, what is second condition? Second condition, the previous path should be ignored. The previous path should be ignored. The previous path should be ignored. Why the previous path should be ignored? I'm just trying out to explain the articulation point so you understand. But we have to just clear about this low value array. Okay, when you find the three things, the articulation point is a simple thing. When you know the three things, then the articulation point is a simple thing. You just find out in a minute. Okay, this articulation point. When you just find out what is your parent array, what is your discovery value array, and what is your low value array. Okay, so So those two conditions apply at every stage. Okay. So the one should point minimum discovered value now. But initially the one is not pointing to anywhere. Okay. So the discovered value of one is one. Initially the discovered value of one is one. Okay. And here also, initially the discovered value of this state. But previous path should be ignored. So this path should be ignored. This path should be ignored. Okay. This path should be ignored. And here also this path should be ignored. So at this stage 3 will point itself, because this path ignored, then the minimum value is its own discovered value. So one is point itself. When one cannot backward, then it point its own discovered value. Same here 3. When 3 cannot 3 will ignore our previous path. 3 cannot go to backward, then 3 should point its own discovered value. Okay, so its low value is 2. And also same here also 4, because it should ignore the previous path. We should ignore this previous call, this previous path. Okay, so we have to just put out the low value is 3. Okay, because it point itself. Okay, because it point itself. Okay, because it point itself. But at this stage also, initially what we are doing, initially we just put out every initially we put out every low value to its discovered value. Because we initially we just put out every low value is discovered value. Okay, because it doesn't have any, minimum path point. So initially we just point out, initially in initial condition we say that our discover value is same as low value initially. But at some condition we change. So initially we just tell out that our low value is our discover value. So same here, so same here, so same here, so same here, so same here. But at some stage, like I'm saying, I'm telling about which stage have to change our low value. So first we have to just put some condition so that you understand. Some stage we have to change the low value according to condition. So first condition, what I'm doing here, we just ignore the previous path now. So what is, if at the nodes, like at the vertex of 6, how many neighbors have 6? Sorry, I'm just explaining at 7, at stage 7. Okay, so how many neighbor of 7? How many neighbor of 7? 7 have 2 neighbors, 3 and 8. Okay, but 3 is our parent. But 3 is a parent of 7, no? But 3 is a parent of 7. So we can, what I'm saying to you, at the stage of find low value, we have to ignore this path, na? We have to ignore this path. Okay, so what we are going to do, if the neighbor is a parent of 7, if the parent of vertex if the neighbor of 7 is its parent, then we have to just continue, because we have to ignore this path now. So how we can ignore this path? We can ignore this path using this condition. If the neighbor if the neighbor is our parent, if the neighbor is our parent and neighbor is visited, then what we have to do? If neighbor is your parent and neighbor is visited, then we have to ignore. For ignore, what we have to put? We have to put continue. We have to put a continue. Okay. If neighbor is our parent and neighbor is visited, then we have to put continue. It means we ignore this path. Okay. We ignore this path. After that, we check out the second neighbor. But what we found out? What we find out? The second neighbor is visited, but this neighbor is not our parent. What we get? We find out that the second neighbor is not our parent, but it is visited. At this stage, we have to change our low value. At this stage, we have to change our low value, because we want to point a minimum value. We want to point a minimum discovered value. Initially what we are doing, initially we point out our minimum low value to discovered value, so that our discovered value is updated as a low value. Initially we point out our minimum value, our low value to discovered value. But after that what we are doing, we just check out when our neighbor is visited and the neighbor is or not parent. Okay, in this condition, if else if our neighbor is not our parent, and it is visited, at this stage, what we have to do? This stage, you know what we have to do? We have to compare the low value of neighbor and itself. Sorry, we have to compare the discover value of neighbor and itself low value and update our low value. Okay, so we update our low value VTC equal to min of this low value and this low value. Means we update our min value according to our low value and the neighbor's discover value. Okay, so discover value of neighbor and our low value. Okay, so according to this we update our low value. So in this condition we update our low value to 6 because this is smaller. Then and same thing here, 6 at the same stage, 6 here as the same thing. How? What is the same thing? The 6 has 4 as a, normally 6 has a 4 as a low value. Normally 6 has a 4 as a low value, and 6 we have to ignore this path. So 6 has a parent 4, but we have to ignore path because neighbor is our parent. How many neighbor of 6? 6 has a 3 neighbors, 4, 1 and 2. But the 6 have 3 neighbors and the low value of 4. First the 6 has 3 neighbors, but 4 is our parent, so we have to continue. We just ignore this path now. We have to just ignore this path. But 6 to 1, 1 is our neighbor, but this is not our parent, and this is your visited. If this is visited, then we have to compare. When we have to compare the low value, and what we find out, the low value of this is smaller. Then we have to update our low value and put is 1. Okay, so you understand? We have to update our low value when our neighbor is not our parent and neighbor is visited. So you just clear out what we are doing. Now you are clearing what I am doing. Okay, so we find out our low values, but some extra thing are and done, that at the time at the stage of traversal, at the stage of DFS, when we call the DFS, what we are saying you, when we call the DFS, so this is the something when we are going to call it. But else if we are calling the DFS, like if we call our neighbors, so how, what we are doing it, what we have to do when we call our neighbors, so we just call DFS to our neighbors. Then after that we have to backtrack it. Okay, first you have to just crop out that thing. Okay, so I have 1 minute, so you have to just smaller it. Okay, so if the neighbor is our parent and neighbor is visited, then we have to continue. And else if neighbor is not our parent, then what we have to do, we have to just update our low value. Okay, then we put else DFS. So after the DFS called of neighbor, after the calling DFS neighbor, we have to update our low value in a post order. In the sense, back in the stage of backtracking, we have to update our neighbor values. Okay, at the stage of backtracking we have to update our neighbor values. What is the neighbor values? At the stage of 7 we update our neighbor values, and here. So at this stage, when we call the 7, this is the last stage, and when we are backtrack it, then we have to update our low value with the comparison of child value. What I'm saying, when we are coming at the stage of 3, then we change our low, then we compare our low value with our child low value. 7 is compared with 6, and we put low value as a 6. Okay, so at the post order of TFS we update the low value. And which is minimum of our values, minimum of our low values, and low values of discover values. Sorry, discover no, low values of neighbor. Okay, so this is our post order. Okay, so same thing here, and we update this 3 with 1 because the value of the low value of 1 is, the low value of 6 is 1 and the low value of is 3. So after comparison in the post order, the 6 is child of 4, so 4 is update our lower value, which is 1. Okay, so you understand what I'm saying? So this is our condition to how to find a parent array, discover array, low array. Okay, so So the last condition is what? The last condition is what? That how we can find the articulation point. So how we can find the articulation point in this part? So for find an articulation point, what we have to do? We have to just confirm how we can. We have to just find out the parent array, discover array, low value array. So what is the benefit of low value array? This point is clear at this stage. So why we are going to find the articulation point? So for this we have to create this path, and again, no, I can explain in this part. Okay, so you just understand. Okay, so but we have to ignore this path. So we have to just clear this all thing. I think we have to just put out another way. Sorry, we want to create it again. Okay, so what we have to do? We have to just take out and create like 0, 2, 3, 4, 0, 3, 4, and this is your 5, this is your 7, this is your 2, this is your 8, this is your connection. Okay, so this is discovered at one stage. Okay, and the low value is 1, and this is discovered as a 2 stage, and low value is 2. Sorry, this is after the updating. Same thing previously what I'm right, same thing is here after the all DFS. Okay, after the all DFS, discovered is a 2 and discovered value is 1. Discovered value is 1. Discovered value is 3 and discovered value is 4, but the updated value is 1. Low value is 1. Okay, and the low value is discovered value is 5 and discovered value is 5, and the discovered value is 6 and discovered and low value is 6. Discovered value is 7 and low value is 6, and discovered value is 6 and low value is 6. Sorry, discovered value is 8. Okay, after the previously what I'm right, you just copy it and find out here. Okay, and what is our conditions? Our condition is what? If our neighbor, if our neighbor is our parent, if our neighbor is parent, if our neighbor is equal to parent and parent it's common that if neighbor is parent, then it would be wasted. Then we have to just continue. But else, if neighbor is not parent, and wasted, then what we have to do? We have to just compare the low value of itself, and then we have to just compare the low value of itself and discover value of neighbor, and we update our discover value. Okay, update our discovered value min. We just put a min, low VTSS and discovered value of our neighbors. Okay, and the third condition is we call the DFS of its neighbor, and in post order we update our low value with its child, and we just update our low value of BTCS, comma neighbor BTCS, low value of neighbor, low value of neighbor. Okay, we just update it. This update after at the time of backtracking we update it. You understand in the previously I'm write it. Okay, but how we can find articulation point? So this is our updated array. Okay, so how we can find articulation point? We tell about how we just find out this low value previously. So we just find out this low value array. So now I'm going to explain how we can find the articulation point at this stage. So articulation point. So if we find out what is our articulation point, then we have to care about that this stage. This four has how many neighbors? This 4 has how many neighbors? This 4 has this neighbor, but we have to ignore this call. Then how many neighbors? The first neighbor is this. And the second neighbor is this. Okay, the first neighbor is this and the second neighbor is this. But what is our condition? Our condition is if our neighbor's low value, if our neighbor is if the low value of our neighbor is bigger or equal, then this is your articulation. What I'm saying, if at the stage of that at the stage if at the stage of post ourselves, we have to do this thing, that if if our neighbor, if uh, like what if low value of its neighbor, sorry, a discover value of its neighbor, if discover value of its neighbor, the discover value of its neighbor is greater than or equal our low value, then this is our articulation point. This is our articulation point. Why this is your articulation point? Because if we talk about the at the stage of 4, the this is your parent, so we have to ignore this path. So after that, the one is the neighbor, the 4 has a two neighbor. This is your first neighbor and this is your second neighbor. Okay, so we cannot when we ignore this path, when we just remove this 4, this graph is divided into two parts. This graph is divided into two parts. This would be artificial point. But why we compare this? Because when we compare, then what we find, this one is cannot be connected at, when we find out the low value of this is 1. Okay, it means it cannot connect it at this stage. It cannot be connected at this, after the fourth value, after the fourth vertex, it cannot be connected, which represent the low value. The low value of the zeroth node is represent the, it cannot be connected at this stage. It cannot be connected at this stage. So if we remove this, then it cannot become here, so that the graph is divided into two parts. If we remove this and it connected with this, then this is not artificial point. But this is not happened. This is not connected with this part. Okay, so this is your artificial point, because the low value of 1 is 1, so it cannot be connected here. So if we remove this part, then it makes another graph. Okay, it makes another graph because it's not connected with, it is not connected with this part. If we remove this part, then it is connected another graph. So this is our articulation point. Okay, same here. 4 here also, here also there are another neighbor, and the value of this neighbor is also greater than or equal low vertex. So this also cannot be, this is also cannot be come here, this is also cannot be come here. Okay, it means when we remove this 4, then this 5 cannot be connected here, because the low value of 5 is 5, the discover value of this is 5. It means it cannot be go backward. The limit of this 5 is here, the limit of this 5 is not backward. The limit, it means the 5 is not connected with backward. If we ignore this path, then 5 is not connected at any other path. 5 is not connected with any other path. So if we ignore this 5, then the whole graph is divided into two parts, which represent the low value, which represent the discover value of this 5. The discover value of this 5 will represent that if we compare with our discover values of neighbor, it means if our low value is 4 and the discover value of neighbors is 5, it means that we cannot connect. If we ignore the 4, then the discover value of 5 is 5. It means the 4, when we ignore this 4, then it cannot be connected the previously. Okay, so you understand what I'm saying to you? Okay, thank you. So this is our stage where I am explaining everything. Okay, so I think we are creating a mistake at somewhere. Oh, sorry. What I'm saying to you is, if we are stage at 5, sorry, I'm just explaining again. If you are just confused, so I'm saying that discovery value of low, like what I'm saying is, like at this stage you are just confused because we just clear about that if our, like at stage of 4, if the low value of 5, like 4 has how many neighbors? 4 has this neighbor, and this neighbor. Then 4 has 3 neighbors. This neighbor is a parent, so we have to just ignore this path. Okay, and this is our first neighbor. This is our first neighbor, and this is your second neighbor. If the low value of neighbor, if the low value of neighbor will greater than the low value of neighbor will greater than of its greater than or equal of its discover value of vertex, like 4. If the discover value of 4 is less than is sorry, the lower value of neighbor has greater than or equal discover value of 4, then this is the condition where our articulation point is found. We telling out opposite because some point. So this is your articulation point if the low value of neighbor was greater than or equal to discover value. Okay, so this is our articulation point. How? If the low value of 5 is greater than or equal of 4, it means it cannot go backward. The existence of this neighbor is that stage, because low value is a value which points a minimum value. Okay, same here also. The existence of this part is not go to here, is not come to here. Okay, so the existence of this node is completely here, it cannot complete here. Okay, so this is the stage that where our articulation point is found. So this is your articulation point. Okay, so another thing is also there are two edge cases also find. There are two edge cases also find out. What is the what type of two edge cases? 1 minute. What type of two edge cases? The two edge cases is like the first edge case is always our parent is find out articulation point. Why? Our at the every stage our parent one is always find out as a articulation point. Why? Because the one has two neighbors, this 2 and this 4. Okay, and we check out that the neighbor if the low value of the neighbor 2 is equal to discovered value of the vertex, so this is your articulation point. And also here the low value of this neighbor, the low value of 4 is a 1 and the discovered value of v is 1, so this is also equal, so this will be articulation point. But what we find out when we ignore this, then they are not articulation point, because this graph is not divided into two parts. Okay, so what we have to do, we have to just figure out, we have to just put a condition. What condition? We have to put a condition is like if our parent SRC equal to -1, it means this is our first parent, because initially we take a parent -1. Okay, in a calling time, if we parent SRC equal to -1, then we are stand at this stage, we are at this stage. Okay, and then we increase the counter, okay, before DFS calls. Okay, then when we call 2 times at this stage, then we find out when we call at this stage 2 times, then if counter value equal to 2, greater than or equal to 2, then this is your articulation point. Why this is your articulation point? Because at this stage when we call 2 times, then it creates a two separated graph. How? We just deal with edge cases. Okay, this is our edge case. Okay, so when we are at this stage, we call out this graph like this. Okay, like this. Okay, then again we call this graph 7, 8 and 9. So here we call 2 times. How? We just call first and we just call second. Okay, first time we call 1, then it call 2, 2 to 3, 4 to 5 and 6, and we cannot call here because this is a wasted. So after that we call second times. Okay, and when we remove this one, okay, then this graph is divided into two parts. Why? Because we call 2 times. Okay, so we just check out that if this graph is called again anywhere, if this graph is called and then again anywhere, then this is your articulation point. Okay, so we put extra check here. Okay, we put an extra check here. Okay, we put an extra check for this condition. Another edge case is found out that how we can count our articulation points. We cannot put a counter when we find out that our condition. We just initially what we are thinking, that we just find out counter plus plus, and then we just update our counter and this print our counter, and we print our counter. But this is not a good thing, because this is a case why this thing is not valid. I'm explaining why this thing is not valid. Because when we are going to do this thing, because when we are going to do this thing, like with this, okay, 1 minute, 1 second, okay, here we just understand. So the 5 is not our articulation point. Why? Because we just explain our edge case here. Why we cannot take counter and update the counter, then we find out how many how many articulation point is found. Fine. At this stage 5, the low value of neighbors, how many neighbors 5 have? 5 have this neighbor and this neighbor. But we have to ignore this call. Okay. We have to ignore this fall. And the low value of the neighbor of 7 is 6, which is greater than the discovery value 5. So this is your articulation point. But if we have another array and the low value of this part is, suppose the low value of this part is 7, then this can also tell that this is our articulation point. Then it says that 5 is 2 times. It's 2 times this is articulation point. It means it count again 5 as articulation point. So it when we put counter here, then this loop will then this if condition run again and again. Okay. Then this the articulation point will be increased. If we have a 2 articulation point, then it increased to 3, because this will check again and again. Okay. So what we have to do, we have to put a visited array. If this articulation point is visited, then when we call again, then it cannot be increase the count. So what we have to do, we have to put an array. We have to put an array here. We have to put an array. Okay. Array at the stage AP equal to 1, or articulation point 1. Anything you can take out. Okay. Articulation point equal to 1, or articulation point equal to value. Anything you can put out. Okay. First you have to just figure out what you have to find out. Okay. So this is our 2 edge cases. Okay. So I hope you understand our edge cases. You have to understand our edge cases. This is edge case of for parent, and this edge case for counter variable. We have to take an array, and in this array we have to increase the value. Okay. In this array we have to increase the value. Okay. Clear? So I'm going to telling about how to code. So now we have to just go and code it. So now I'm going to code this problem, so you just understand easily what I'm going to do here. So we take a disk src equal to low src. Okay, it means what I'm doing here, I'm just explaining, equal to plus timer. Why we are taking a timer plus plus, I'm just explaining here. Okay, so in this part we take a initially what we are doing, initially we take a low value equal to lower vertex value equal to discovered value. Why? Initially it will point itself. Okay, so we take a low value equal to discovered value, and what we do, we increase the timer globally. So you just update 1 2 3 4 5 6 7. Okay, so we are taking this. Okay. So we just update our timer, and then what we take a counter 0. Why we are taking counter 0? We are explaining our edge case, which is parent. For this we take counter 0, because we want to check out that if parent call 2 times, if parent can call 2 times, then it is our articulation point. If parent is not calling 2 times, then it is not articulation point. Okay, this is our edge case. So this for it e equal to 0, and if e less than g src dot size and e plus plus, then what we have to do, we have to just find out our neighbors is like g src e, and then what we have to do, we have to check out. So what we are doing, we just find out our neighbor, like what is our neighbor. Okay, so we found out our neighbors like 0 1 0 2 0 3, so we have to find our neighbor. Okay, and then first we have to just put out a visitor to for our neighbors. Okay, for our source, when we are going to at every source, we have to make a visited. Okay, then we call our neighbors like 0 1 0 2 0 3. Then if our neighbor, if our parent src, it means if our neighbor is our parent, if the neighbor is our parent, it means the parent of source is our neighbor. The parent of source is our neighbor. Then we have to continue. Why? Why? What is this stage? At this stage. At this stage, like if we call 2, then what we found? 0 is our parent. 2 has how many neighbors? 2 has 0 and 3 neighbors. And 0 is our parent, then we have to ignore this path. We have to ignore this path. So we will continue at this stage. We will continue at this stage. CONTINUE. Okay. We have to continue at this stage. And after that, what we have to do? We have to do else if. Else if. What is else if? If visited of neighbor, else visited of neighbor equal to true. What is the condition? Why we are putting this condition? We are putting this condition because at this stage what we are doing, if 2 has how many neighbors? 2 has this neighbor, this neighbor. But if this is not a visited, this is not a visited, so we are putting this condition. If this is a visited, like at 4, what we are doing? At 4, when we are ignoring this path, at 4 when we are ignoring that part, then what we get? 4 has 3 neighbors, this neighbor, this neighbor, and this neighbor, and we find out that this neighbor is not visited, and this is your parent, but this neighbor is visited. So for finding this neighbor, we are putting this condition. Okay, so we are going to check out why we are putting this condition. Now we put this condition, and then we update our low SRC according to our minimum value of neighbor, minimum value of low SRC, and comma discovery value of neighbor, okay. So we are updating our low value of SRC according to our discovery value of its neighbors. At this condition we are doing this thing. Okay, then after that what we are doing? We have to just put our neighbors array. We have to fill out our neighbor array. Okay, after that we have to fill out our neighbor array. Then we call a DFS. We created our parent array at this stage. Okay, and then we called our DFS. Then we call a function again which makes a DFS call. Bridge G comma disk comma low comma parent comma a point comma visited comma SRC. Okay, so we are calling this. Okay, and after that what we have to do? We have to just update our low value, what we are telling in the graph. So we have to just update our low value, and with low of SRC comma disk of NBR, and then what we have to do? We have to check and at this stage. And after that what we have to put an extra condition. What condition? If our parent SRC equal to -1. What is the signal of this condition? The signal of this condition is that our source is starting. This is the condition where our initial source is starting. At this stage we have to just count how many times we call it, how many times we find out our initial source. And then if we call 2 times from our initial source, then it means that this is our articulation point, because it makes a separation of graph. We are telling about in our explanation part, so I hope you will just watch it. And else if low of neighbor, and else low of neighbor, and this is a condition where our articulation point was decided is greater than our discovery of SRC. Okay, so this is the condition where we put out condition. This is the condition where articulation point is decided. Then we put a point of SRC equal to true. Okay, so this is the condition we are checking about. So initially we take a discovery array and we take a low array also, and we put a timer so that we can count the timer in counter equal to 0, and we put a visited SRC equal to true, and we put a loop to find out all edges, and then we put a neighbor, we find out our neighbors, and we put a p if parent of SRC equal to neighbor, then we have to continue. And then if our neighbor is visited, then what we have to do, we have to just update our low value, and else. And after that, what we have to do, we have to create our parent array, and then we call it, and then we update our low value in a post order, and then we have to put our condition for parent array. Like if our source is starting point, then we have to put an extra condition where a point is updated, and this is the condition where the a point is decided at this stage. Okay, so this is our condition, and we just run it, and we're getting error. I think we are getting error 49. We're at 49. Why I'm getting error? Errors expected at the end of output. What does mean? So I think we are not creating an extra check. Sorry. So I think what is error? Oh, sorry, we doesn't put a comma here, so we'll just put comma and then run. So it's accepted, and then submit it. This is correct answer. So now we have to just go and just go through this code to understand clearly. So now what we have to do, we just crop this code. Okay, we just crop this code. Okay, so what we are doing initially, first we raise this thing, we raise the all part. Okay, so this is our 1, this is 0 vertex, this is 2, this is 3, this is 4, this is 5, this is 7, this is 8 to 8. So initially what we are doing, we just initialize the discovery value of vertex as low value, because initially we update our low value with the discovery value. Okay, and then int counter equal to 0, it means we update our counter according to our calls. Okay, for a edge condition, for a source condition, edge condition, like initially we find out the source is articulation point according to this algorithm. If we are not using this algorithm, this condition, then 0 is the articulation point. For this we use this condition, so that we put a counter equal to 0. Okay, and also then we put a visited SRC equal to 2, then we put 0 as a 2. Okay, after that we call our edge, we take a 2, we call our edge like 0 to 2, 0 to 4. So then what we are getting, we just check out the parent of SRC equal to neighbor. So we found out that all neighbors is our parent, not the all neighbor is not our parent. Okay, this is not our parent. Okay, so we just continue again, and we find out that, so this is not our parent, so we don't continue, we just check out this else if condition. Okay, in this else if condition we find out that this edge is not visited and this edge is also not visited. So we check out this condition, and then we reach out an else condition. Okay, in else condition what we are doing, we just made a parent of NBR. Okay, so initially our SRC is what, -1, so we put a -1 as a parent. Okay, we put a -1 as a parent, and then in AP bridge G disk low parent adjoint, we call the depth first search or neighbor 2. We call the neighbor 2 as a depth first search. Okay, so 2 will call again, and then we put out here, we call again, and we put out discover value and low SRC value and timer. Okay, according to timer this is 2 because 1 is updated. So where we put a 2 as a discover value, which is 2, and then we put a visited 2. Okay, and after that we find out all edges 3 and 0 1, and we check out the parent SRC equal to NBR. Yes, this is a parent. This edge is a parent. So we continue, and we find out second edge. And in second edge, what we have to check? We are checking out that if the low SRC, this is visited or not. First we check this is visited, this edge is visited or not. But we find out that this edge is not visited. We find out that this edge is not visited. When this edge is not visited, then what we are checking out? When we just move out here, okay, and what we are checking, this parent is if parent of SRC equal to -1, no, this parent is not a -1, okay. And then we check out here, and we check out that this is our articulation point or not. We find out that the lowest value of 2 is not greater than or equal our discovery SRC. It means the discovery value of 2 at this stage, the discovery value of SRC is not less than or value of equal to low SRC, low L1. Okay, so this is not a articulation point. Same, but here at the stage of 4, this condition will run. Why? The discovered value of SRC is 4. The discovered value of SRC is 4. And it has 3 neighbors. It has 3 calls. It has 3 edges. The first edge is this. The second is this. Third is this. Okay, but this is your parent, so this will continue. It goes to this. It goes to this edge. Okay, and when it goes to this edge, then it calls. And but we find out that this is a visited. And this is visited and we are equal to 2. This neighbor is visited. So this condition will run. This condition will run, and we update our low value. We update our low value and make 1. Okay. And then we update our low value. Okay. Then what we are taking? Then we come out at this stage, and we reach out, and we come out this stage. Okay. And then we again run this loop. Okay, and then we again run this loop. Then what we found out that this will continue because this is not our parent. And then we come here at this stage, and this neighbor is not true, and then we are coming at this stage, and we make SRC, equal to true. We make SRC equal to true, and then we call again called it its neighbor. Okay, to 5. Okay, but when we backtrack it, when at the stage of backtrack it 4, because at the time of backtrack now 4, if we have to backtrack 4, and we update our low value, and after that we checking our articulation point. At the backtrack condition, we checking our articulation point, but we have find out that our low is greater than or equal discovered value. Yes, our neighbor 1 value equal to our 1, because the low value of this is 1 and this neighbor is 1 also. So this is not an articulation point. Okay, but this 5 is an articulation point. Why? Because this condition will run for 5, because the low value of 5 have 2 neighbors. 5 have 2 neighbors, 4 and 7. The low value of 4 is 1. The low value of 4 is 1. The low value of 4 is 1, and the low value of 5 is 7 also. But we cannot call here, because this path should be ignored. Because this is a parent call. Only we have to check at that stage. Okay. So what we find out that at the 7, 6 is our low value. 6 is our low value, which is bigger than 5. So this is bigger than 5. It means it cannot go here. It cannot go backward. It always, the existence of 7 will be here. So that the low value of this is 6, which is bigger than our source value. So this is our articulation point. Okay. So I hope you understand what I am saying. So thank you so much.